Hello everyone. Hello everyone in the fourth episode about .NET GC internals. Today we are covering the plan phase. As you see, the name is the plan phase, and I hope you will learn a lot about the plan phase, what it is, for what it is used, and let's move on simply without further delays then. And just as a recap for the whole thing, let me switch to the slides. We are inside somewhere in the middle of the .NET GC internals mini-series. Say hello from where you are, because as always I really like to hear that you are there and from where you are watching me now. So hello everyone again. As I said, we are in the middle, somewhere in the middle. Today we are covering the plan phase because recently I covered mark phase, so we all know, if you watched the previous weeks, we know as how the objects are being discovered, what is the reachability, and how the GC discovers that. And now we need to think what the GC does with this job. By the way, you can also give me a feedback whether you hear me well or not, because previously I forgot to set up my mic, so I hope you hear me better than the previous beginning of the previous webinar. So okay, let's just move to the main part. So we have the plan phase: gaps, plugs, plug tree, brick tables, a lot of interesting knowledge that is not well yet covered in many of sources about the GC. You will hear about marking, sweeping, compacting, but the plan phase is super internal part of the GC in .NET, not well documented. In fact, when I was discovering all this stuff for my book, I was just literally debugging GC line by line for weeks to understand plan phase. And today I will just show you what is the result of all this research, what the plan phase is all about. So, as I said, we have covered the mark phase. The mark phase is all about discovering reachability. So, from the perspective of the GC, at the very beginning, we have continuous memory region containing of objects, and at some point in time the GC kicks in, the object graph traversal is being done, so we mark objects that we have visited. As we know, the marking happens inside the method table pointer. So in the end, after the mark phase, whether it is a phase which is concurrent or not, the result is we have somewhere stored information which objects are reachable and which are not. And those which are not are the garbage that we would like to reclaim memory after them, like CNF in this scenario that we are looking here now. So okay, the GC now knows what is garbage to be garbage collected, what is live, it cannot be reclaimed, and now it needs to make a decision, and it has two options. First of all, and this is kind of spoiler, it can sweep. So because I will cover sweep phase in details in one of the next webinars, but it can sweep. So sweeping is pretty easy. When we discover that, for example, object CNF is no longer needed, we know this, so somehow, magically, I will cover that, it marks the place after CNF as a free space that can be somehow reused. This is super fast because it doesn't incur a lot of memory movement, let's say. We somehow only mark this space to be reused. We call it free space, gaps, however. It introduces fragmentation, so it is not always the best choice the GC can make. The second choice it can make is compacting, which is kind of something that we will do while we move Lego bricks, and we would like to get rid of some of them. So after discovering CNF is no longer needed, we compact the memory simply by moving objects together close to each other, getting rid of the space that is no longer needed, exactly as we would compact Lego bricks, taking out CNF. This incurs a lot of memory movement because we need to copy memory, copy objects, so this is optimal in terms of the result, but it is much bigger overhead in general to compact. So the obvious is not choice. The GC kicks in, it knows what the garbage should be collected, but whether the compacting should happen or maybe sweeping will be just enough, this is now the decision of the GC to take. And we need to make this decision. The GC could guess, the GC could take a random decision. This is also a decision, but obviously it is much better to take not even an educated guess, as it is called, but to have good knowledge or even 100% certain knowledge which decision is better in terms of some heuristics or numbers or any other measurements. So for taking this decision, the plan phase is introduced in .NET. This is the phase that is taking this decision, calculating everything that is needed to make this decision, whether we would compact or sweep. Because of that, most typically when you will read about GCs and garbage collection in general, you will see the mark phase, compact phase, sweep phase that are described in theory, but the plan phase is pretty implementation detail of the .NET. It is not something that other runtimes can do it totally different. This is how plan phase looks in GC in .NET, and this is how .NET GC is calling it. Other algorithms, other runtimes may call it totally different. This is the GC thing, the .NET GC thing. Okay, what is super interesting about the plan phase is that it not only calculates which decision is better, but it calculates everything to make compacting or sweeping. So it is not kind of let's look around, compute something, compare some numbers, and then I know I should sweep, so now I will take everything that is needed to sweep. But plan phase is doing both things in the end at the same time. So it doesn't only know which decision is better, but at the hand he has the data needed to sweep or compact. And this is super interesting that it is done in that way. How it is done, this is the goal of today's webinar. So, one another side note, this is happening in the pause phase, because it would be super hard to implement all this stuff during the regular concurrent way of working the application. Plan phase is at the non-concurrent stage of the GC, so during a pause, we pause all managed threads, we pause our application, and the plan phase may happen. So the faster plan phase, the faster pause, the shorter pause. So plan phase should be really optimal, not to introduce long pauses. Okay, that was an important side note. So how it is all happening? We know that the objects are seen by the GC as a continuous memory region, and after the mark phase, we know that some of them are marked as those reachable. So we know that already. For the purpose of this webinar, I'm marking marked object as a dark gray, and those which are not reachable are this light gray. So those are reachable objects, the dark gray ones, and those are some not longer reachable objects. That was discovered during the mark phase. And now, super important concept, the plan phase groups those into so-called plugs and gaps. So every continuous region of no longer reachable objects is called gap, and every continuous region of marked object, so reachable object, is called a plug. So in the end, what the plan phase is doing for its purposes is to group all that. It simply needs to group that into the pair of gap and plug, gap, plug, gap, plug, gap, plug. There will be just continuous interleaved gap by plug, and that's for the whole region that we are interested in. So how it is happening? We could think about any magic happening here, but no magic happens in the end. We need simply to scan memory that we are interested in, the memory region that we are interested in, object by object. Simply discovering that we are just inside a gap or inside a plug. So from the very first object in, let's say, generation 0, because we may be interested only in generation 0, we will start from this object, which means we will start from looking at this pointer, which is just treated as a beginning of an object. We will see that it is not marked. We have this knowledge either in the meta table pointer or in somewhere else if it is a concurrent GC. Concurrent mark, but we know it is not marked. We know that we have created now a new gap. It is a beginning of a new gap. Then we jumped to the next pointer and we discover, okay, but this one is marked. So now the gap has ended and the plug begins. Then we jump to the next one and again we see, okay, but the plug has just ended, a new gap starts. And so on and so on. Next time we will jump to this one, we will see it is still not marked, so the gap is from here to there. And then we will mark from one object to another. We will just scan all those objects one by one, grouping them into the gaps and plugs. No super rocket science, right? The only thing that is happening here that may be interesting for us, that it requires pretty a lot of memory accesses, because we need to scan the region that we are interested in object by object. If generation 0 contains 1 million of objects, we need to scan them one by one. In the one small side note that will explain why not necessarily it happens. There is important optimization, but conceptually we can think about it like that. We need to scan all those objects one by one. And yes, very good. There are some questions, so I didn't say that explicitly. Do not hesitate to ask, so I will answer all the questions, although immediately or maybe after the webinar. If you have some questions, ask. So I'm super happy we have some questions. So the very first from Laszlo is, do we need to look up the object size? Yes. The question is how in the end the GC traversing the objects is knowing by what size it should skip. And this is by looking into the metadata of an object. So because GC obviously has this pointer, and this pointer points to metadata, and the metadata knows the size of these objects. It knows by this single indirection, looking at the metadata, what is the size of the object, and it can just jump into the next object. And here we have the same question. So yes, method table is a pointer and pointing to a metadata, and this metadata contains the size of an object. So a lot of metadata accesses also is happening here, because we need to access metadata of every type that we are touching here during this traversal. But this is what we need to do. And from now, the whole plan phase stops to think about objects, but starts to think about gaps and plugs. It will be no longer interested in considering single objects. Now, if it will be interested in moving something, it will move the whole plug, not a single object. If it will be interested in pinning something, it will pin the whole plug, not a single object. From now on, the plan phase and the whole GC happens at the level of plug and not a single object, which is obviously a good optimization, because we expect objects are grouping together, live objects are somehow grouping together, so those plugs will be bigger than a single object, so we will operate on plugs, not on a single objects, so much less in quantity data to handle. So yes, then one optimization, because I said that they are scanned by object, but we can make here one nice optimization to omit scanning gaps object by objects, and here we return to the mark list that we covered at the webinar about the mark phase. Then I mentioned that while we traverse the whole object graph and while we mark objects, there is this additional step that we add an address of currently visited object to some mark list, which has a limit in size, but unless it is not overflowed, we add this address to the mark list. This gives us really nice optimization, because then if we will sort this mark list, and we are sorting this mark list at the end of the mark phase, before plan phase, then we have now sorted list of our marked objects. So instead, and this is nice, because if we are at the end of the gap, at the end of the plug, and we start to consider a gap, instead of going through all the objects, we just can directly jump to the next marked object, because we have it as a sorted list inside a mark list. So mark list allows us to skip scanning of gaps and only scan plugs. So it is kind of nice optimization that we can have, which is obviously important, because as I said, plan phase happens at the non-concurrent phase, so every optimization that reduces the pause, and this is during the pause, is welcomed, really. So that's why we like mark list optimization. Just a side note about this mark list, it is only for ephemeral GCs, so only for generation 1 and 0, because as the comment in the code itself says, for the full GCs we have multiple segments, so there is possibility that the generation 2 contains of non-continuous memory regions, which complex things, and more likely also the mark list will overflow, because if we start to consider the whole managed heap in the full GC, probably the mark list will overflow. So this is optimization, and on the end, typically generation 2, which is called full GC, is a concurrent one, so reducing pauses is here a little less important. At least from this perspective, so it is only for Gen 1 and 0 optimization, but still super nice to reduce the pause introduced by the Gen 0 or Gen 1 GC. It is also not for the background GC. If maybe simply saying that in other words, if the background GC is running, we don't use mark list. Also not to interleave data structures and all the concepts while the two GCs are running, and the background and foreground GCs is another topic. We will cover that later, how they cooperate. So but for the foreground regular ephemeral GCs, mark list is very nice optimization, and by vectorizing it, as I described it in 2 weeks ago, we are just making it faster, because we are faster sorting the list, so it is shorter pause, and also because of that we can use bigger mark lists, so more commonly we will use it for less object scanning for gaps, so again shorter pauses. But it is just a side note about the mark list usage. We can live without mark list. The whole concept is just to split and group all those objects into the gaps and plugs. So in the end we have a gap, plug, gap, plug, gap, plug. And now for every of it we calculate 2 super important things. For every gap we calculate the size of it, which is super easy because we know where it starts and where it ends, so calculating maybe is too complex word. It is just subtraction of 2 pointers, or we can track the size during building of the gap, so this is a super easy thing. We just store the information, what is the size of every gap, and for every gap we know this information. Pretty easy to get. Then For every plug, we calculate the so-called reallocation offset, and this is a little bit more complex to calculate. The reallocation context is the information by what number of bytes we will move this plug if we decide to compact the whole thing, the whole region that we are considering. So as you see, this is a calculation. Even without moving things, we are getting information needed both for sweep and for compact. Because if we decide to sweep, we will just move gap by gap and make a free space from every gap. We have information about the size, so we can use this information. If we decide to compact, we will ignore gaps, but we will move plug by plug, and we will reallocate every plug by the amount of bytes that we have already calculated. So compacting also doesn't sound as a complex thing if we have this information already computed. And so in the end, we have this information for every gap and plug pair, because this is the whole assumption that every gap is followed by a plug. So we are storing two pair of information: size of a gap and the reallocation offset of a plug for every such a pair. And that's pretty nice. This assumption is valid because you can think, okay, why we can make such assumption that every gap is followed by a plug, and that maybe we have allocated an object here and it is just reachable, so why I can assume here is a gap. But this assumption is valid because every generation starts with an artificial gap with the size of a minimal size of an object, so 24 bytes of an empty object that there is always at the beginning of every generation. So in the end there is always one gap at the beginning, and then there will be some plugs and gaps and plugs, but we will have this gap artificially created. So for that we have it. And if you will, for example, analyze memory dumps, you will always see that generation at the beginning, even if the generation is empty, has this one single object that is there for that purpose, for the future usage. Okay, and again, if you have any questions, do not hesitate to ask. So now one important question is that you can ask how we calculate, because we know that, okay, gap sizes are easy to calculate, but how the offsets are calculated, how we can know that this is 24 and 18 and so on and so on. Looking at this simple scenario, it is not so super hard to calculate, because we know that we can just, for this, for every plug in the end we need to sum the size of gaps that are preceding them. So for this is 24, for this plug it is the size of this and this gap, for this plug it is the size of those three gaps, because we are just getting rid of gaps and moving all the plugs to the left. This is obviously conceptually super easy to say, but to make it as an algorithm which is general is not so easy, and it takes a lot of the plan phase to make this happen. And in the end we can say that this calculation of the reallocation offset is just an allocation. What in the end we need to know is where we would like to allocate some region. It happens that we are to allocate a region which is just for our plug, but in the end this is just an allocation. So the reallocation offset calculation is based on an allocator inside the GC, and this is the same allocator used in other purposes when we are trying to find some space for an object. So it is reused here in a way that for every plug we are firing this allocator and trying to find a place for it. In such a simple scenario as here, obviously it will be just that every plug will be allocated one after another, so we will end in the same result as we expected. And this allocator is kind of the most typical one trying to allocate objects by objects if there is space for that. That will be the result. Two important things and results from this slide is, first of all, that all this is happening kind of on the side, virtually. We don't move anything, we don't allocate anything in terms of making a memory. It is called allocator, but it is just an allocator, this part of allocator that finds place but not allocates anything yet. It is just finding an allocation place when it would be nice to allocate it. So it is all happening virtually on the side with the help of all the allocators data internally used by the allocator to make those reallocation offset calculations. Which is nice, because we are somehow allocating something without making those allocations, only to calculate the resulting offsets. Because what in the end we have is just the new address, we are just subtracting it with the old address, and we have the reallocation offset to put inside our plug info. So this is one important finding from this algorithm, and the second is that with the help of that we can pretty easily calculate the compaction efficiency, because so we will know by which by what number of bytes in the end we will reduce the size of the heap if we decide to compact, because the compaction efficiency will be just the difference between the current size and the size of the heap after compaction, which we know because it is just the space after the just virtually allocated object. So we all know this without allocating and doing anything. It's all happening in memory. So we also know the compaction efficiency, and this compaction efficiency will be super important measurement to make a decision whether we should compact now, or maybe it's still enough to sweep, because we all know, as I mentioned shortly, all has both compacting and sweeping has good and bad sides. So the compaction efficiency will be an important input, whether it is worth to compact at all or not. So this allocator inside finds this reallocation offset. So in the end, we have this information for our, let's say, generation 0. For every gap and plug pair, we have this information. What is the size of the gap? What is the reallocation offset? Now, another question, where we do store this information, where we do store information about the size of the gap and the allocation offset. And we could imagine it is stored somewhere else on the side in some data structures internally in the runtime, in double linked list, because it is super nice data structure, wrapped inside some nice object-oriented design probably. But this is not how we think at the level of so tremendously demanding thing like the GC. So here we are mostly concerned about the memory access patterns. And the memory access pattern here is that we have already touched those objects. We have already read meta table pointer because we were interested in sizes of the objects. So for sure we have touched those that are at the beginning of plugs, for example. We can say that for sure we have read already from memory places like here, somewhere here. So cache lines and caches are warmed around these memory regions because we have already scanned those objects during our plug and gap creation. So if we have already warmed our caches around this memory, it is worth to reuse this part of memory. So instead of keeping all this data that I mentioned somewhere else, we will reuse the managed heap itself for storing it. And this is why we store all this information on the managed heap. And when we can store this on the managed heap in a safe manner, we can store it in gaps, because gaps represent the part of the memory that will be no longer needed. So we can write here everything we would like, and our code will no longer access this memory, so we can overwrite with whatever we want. So we have those gaps that we can use for the information about all those planning phase results. And exactly this is happening in this implementation. We are storing this information in plug info, which is in the gap. And exactly to be more precise, it is at the end of the gap preceding the plug, because every plug has a gap before. We store this information that we have found at the end of the gap before the plug. And this is nice, because we have somehow touched this memory region, so it is enough to use it, and we should be happy. And what we store there? We store there the gap size, as I said, the reallocation offset. Another thing, both are word sized, they pointer sized, because we expect reallocation may point to any in the space, address space. Also the gap size, do not limit it, so they are pretty big. So we have already 60 bytes are used for our plug info, because it is also somehow called plug info. All gap reloc pair, this is the official name in the source code. Then we also use the next 8 bytes for left-right offset that I will cover soon for why we are using these offsets. So in the end, all this plug info takes 24 bytes in case of 64-byte runtime. 24 bytes for storing a plug info before every plug at the end of the preceding gap. So in the end, when we look at the result of storing all this information, it will look something like that. We will have the plugs, and at the end of the preceding gap, we will have the data storing this information. We overwrite the gap data. There were some fields of some objects, some references, but we don't care, because those are gaps. So those objects will be no longer used. So that's totally fine. This is also one of the reasons why the minimum size of an object is 24 bytes, because we need to have this space for every plug. And if an object could be smaller, and then it would form a plug, and then it would form a gap, and then followed by a plug, but if it would be smaller than 24 bytes, we will not have a place for the plug info. So we need to have the object size to be no smaller than the plug info size, which is 24 bytes. That's why the minimum object and object size in .NET, in case of 64-bit runtime, it is 24 bytes in size. It is a header, 8 bytes, method table, another 8 bytes, and an artificially added 8 bytes just for the purpose of making it 24 bytes, even if it has no fields and any data inside. So this is one of the reasons. I mean, maybe the only reason. I'm not sure if the only, but for sure one of the main reasons. Then another side note is that, as you see, we overwrite some data here. So during this plan phase, we are just without problems and without any fear overwriting some data inside the gaps, because for the code it doesn't matter, but it might matter if you are, for example, interested in analyzing this. If you take a memory dump of such an application, which is at the state of planning inside the GC, you will take a memory dump with this view, so some data will be overwritten by this plug info. And because of that, the tool that you would be interested in analyzing the, for example, object graph will be not able to do that in a true manner, because we have just overwritten some, for example, references that were there. So the object graph will be destroyed. from the perspective of the full object graph traversal. And this is why if, for example, you take a memory dump and try to analyze it in a WinDBG or in any tool, because currently we can use CLI tool for the dump analysis, and try to do any analysis that requires some traversal of data and between objects, you will see that it is, in case of the SOS extension, you will see that sorry, but it was taken during the plan phase when it is not valid state, while it is not valid state for traversal, just because we have just overwritten all this thing. So that's why, sorry, you need to repeat, simply make one more memory dump to analyze it and try to be lucky enough to not hit plan phase again. Okay, so we know already that those gap and plugs pairs are stored on the managed heap itself at the end of the gaps. This is nice. Now the left and right offset. What are they used for? So just take they are used because now we have all the information on the managed heap. We have for every plug this information, but we don't have any entry point how we can access this information. We need a list somehow to store, for example, a list of every plug. So in the end, we would need somehow to traverse it when we would be interested in going through all the plugs or discovering a plug for a given address. Then you could scan this list and find this plug in a linear time. But there is an important optimization for that in the .NET runtime, and for that we are building a binary tree of plugs in the end. And the left and right offset is just the offset to the next plug within this binary tree. So having this example with addresses now, we have 3 plugs and they form a binary tree conceptually. And entry 1 will be the center one, which is just under this address. So we can treat this as an entry point. And if you would be interested in knowing other plugs in this particular region, we can treat this plug in the middle as an entry point. And then it keeps an offset to the left and to the right plug simply. So while that's why we have those offsets to the left and to the right plug inside a plug tree, because this is forming binary plug tree that allows us to traverse all the plugs within a given region in a logarithmic time, not in a linear time, which is super nice optimization. This binary tree is balanced, so while building it is tried to be balanced. DC tries to build a balanced tree to have this optimal navigation through all the plugs. So in the end, those left-right offsets allows us to find the plug within this. This is just the information when the child nodes are kept, when the child nodes are lying related to our current entry inside our tree, just to build a binary tree. So this is for building the binary tree. Every plug has a left and right offset. Obviously the child ones will not have, the leaf ones, sorry, the leaves of this tree will have those offsets set to Z because they have no children, so there are no offsets. They are just the leaves of this binary tree here. Another thing now is then who keeps information about this root. to have this entry point somewhere stored. We could imagine a huge binary tree for all the plugs inside our managed heap. We can imagine storing a huge plug tree for all objects inside a given generation, for example generation 0. But we can have millions of objects in generation 0, so then we would have a binary tree for millions of plugs, or maybe less. It depends really on how the data is laid inside. So would we be kind of optimal, let's say, to scan the whole object, to scan the plug tree for all those objects. So because of that, we have the concept of brick table and bricks. So we are, to put it simply, we are splitting the memory region in every generation, in every whatever. We are splitting the memory regions with objects into bricks, which are 4 kilobytes in case of 64-bit runtime and smaller in case of 32. So, but let's concentrate on the 64-bit runtime. So every brick is just 4 kilobyte of data. Like here, we have here one, maybe I will switch to drawings. So we have here one brick which is 4 kilobyte of data. Here here is the end of another brick. There another brick starts, so we have 3 bricks, but one full brick is visible here. Inside there is all this thing that I've currently so far described. So we have gaps, we have plugs. Before every plug there is this plug info stored. So in the end it may look like that. We have a lot of gaps, pretty big ones, some plugs, and then we have this brick which is 4 kilobyte, and for every brick we have an entry into something which is called a brick table. Every entry in a brick table is just a root of our plug tree for this particular region, simply. So in the end it is an offset inside our brick tables, inside our brick. So if we have an address like that, it means that it is this offset plus the address beginning of the whole plug, so plus this one, and this will be just the address of our root of our plug tree, which will be 1, 6, 4, and 0. This is -1 because of the reasons I will not cover. So maybe I will cover, but not now. So we just calculated, okay, the root of our plug tree is there. And because of that, for this given brick entry, we called it brick entry. The brick entry, saying it again, is just a pointer that we can calculate, a pointer from it pointing to the root of our plug tree. So in the end it looks like that. Because we have here 6 plugs, and they are balanced by the GC is creating plug tree that way. It is balanced, so our brick entry points to the root, and then this root has an offset to the right, to the left, and then this one is again pointing to the left, to the right. This one is pointing only to the left because it has no right child. In the end we have such a plug tree for this particular brick, which is nice because now we have only 6 entries in our plug tree, and we can traverse this plug super fastly by only 2 jumps in directions to find a given plug from the brick table. Okay, so I hope it is clear. If it is not, just do not hesitate to ask. I would love to leave you with the understanding of it, because it is so hard of the GC that not understanding this party would be really sad for me. But okay, we can say we have a lot of things here that sounds like optimization. We could simply store a plain list of plugs to linearly scan them, and it will be enough. Why we are bothering in creating all those binary trees here, brick tables, and so on and so on? Why we are so concerned in optimizing all this stuff? And this is because when the compaction happens, we are tremendously often interested in an answer to the question, what will be the new address of the object at a given address X? Because if we are compacting, we are moving objects around. If we are moving an object, it means, and this is live object because we are moving it, so it means it is reachable, so there is at least one reference to it from somewhere. So if we are having an object here and their address x, and there is at least one reference pointing to it, or maybe more, so if we are going to compact, it means we will move this object somewhere else to an address y. So now, even before we are moving this object, we need to update this reference to point to y. So every reference that we have in our application needs to be updated. For every reference that we have in our application, we need to calculate its new address. And you can imagine you have a huge number of such references. Every reference needs to be updated on the stack, inside your fields of your objects. The whole managed heap needs to be scanned for references to be updated, and so on and so on. So a lot of updating of references because of that. That's why the answer to this question needs to be so fast, because it is so often asked. And with the help of brick tables and with the help of plug tree for every brick, we can answer pretty fast. And with the whole concept of plugs, because we are not concerned about particular objects, but in memory regions. So if you have an object with address x, and you would like to know what will be the next future address of it after compaction, you need to calculate the brick table entry based on this address. But this is super easy because we are splitting the whole managed heap to 4 kilobyte memory regions. So if you have an address, you are just dividing this address by 4 kilobytes, and then you have the brick entry index, because every successive entry in the brick table is the next 4 kilobyte memory region being covered. So this is super fast. Then edge case that I need to mention: if the brick table entry is less than 0, it means that, okay, we are considering a brick entry with plug so big that it spans over this brick, and in general it is end of a plug that started in one of the preceding bricks. So by negative index it simply means, okay, but this brick is covering a plug that started somewhere else, so you need to jump over to this particular brick table entry, and there will be a beginning of this plug. So this is a kind of the edge case. In the end, we will end with the brick table entry which is bigger than 0, which now means we need to start to traverse this plug tree, and then we will just have information in the reallocation offset in the plug that we will find. So just to draw it, imagine that you are interested in a future of address of object which is lying here. So we have an object with an address x here. So first of all, we are splitting the x by 4 kilobytes to know that it is an entry in our brick table, and this will be the entry. That's easy. Then we start our traversal. We start until we will find the plug that contains our address. So we will start from the root, because we always need to start from the brick table entry, and then we will jump to the right, but we will see that, okay, this is this plug, but it is too far, so we will jump to the left, and we will see, okay, we are inside the plug that contains our address, so this is the plug we are interested in, and we take an reallocation offset from our plug info, which is just a number, and let's call it R, and our future address will be simple, our old address minus plus, depends how we store it, with our reallocation offset. And that's all. So with the help of pretty small number of operations, we are able to calculate the future address of every object, of every reference that you can meet in your application. which is nice. And because we are storing it for the whole plug, every object that falls within this plug will have the same reallocation offset, so it is an optimization. Like not storing reallocation offset for every object, that would be overkill. This obviously reduces flexibility of moving objects a little, because now we start to consider the whole plug to be reallocated, and this may introduce some problem with fragmentation, because GC is less flexible. If a plug is big, it will just try to compact the whole, move somewhere the whole plug. It is not in force to split plug into smaller ones to fit them somewhere. If there is a plug and it is a big plug, it will be just less flexible to move it somewhere. But it still pays off because it produces so nice way of calculating this new address. And as you see, this all is happening on the side. Even before we start to move objects around, we have the all information that is needed to update references. So we can scan all the references in our runtime, in our application, update addresses, update those references, and only after that we can really move those objects to their places. That's nice. This will be covered in the week when I will be describing the compaction phase. But in the general, this is the whole concept. So again, that's super nice. Also, brick tables are used in translation of the interior pointers, exactly with the same mechanism. As I said, if we can just exchange it and use the same mechanism for finding an object pointed by interior pointer, because interior pointer points inside an object. So inside an array, or inside you can point a field inside an object. So having a pointer, we need to find an object that contains this pointer. If bricktable and all this plug info is not available, unfortunately, if X is an interior pointer and you would like to translate it to an object, you need to scan the whole memory, because you need to start from somewhere, and object by object find the very first object that contains your pointer, which requires a lot of scanning. That's bad. This is happening during the mark phase when you interpret interior pointers. But luckily, after the plan phase, when we reallocate things, for example, we have all this information in place. So if you have any interior pointer X, and then you would like to find an object for it, you can take a proper bricktable entry, traverse your graph, find a proper plug, and only scan the plug. And then find an object from this plug. So much less scanning, because you don't scan the whole brick, but only a given plug. So this is nice optimization also for an interior pointer interpretation after the plan phase, when all this data is available as a additional benefit, let's say. Okay, so here we have all this data: plug tree, gaps, plugs. This is the whole plan phase in the heart of the GC. This is how it is working. I promised also explaining, or at least I promised myself explaining, the left bit and realigned bit, because I mentioned that the plug info contains the gap size, reallocation size, left and right offset. We have already covered that. But they are also those two little bits used for something. And those two little bits are the lowest bits inside the reallocation offset, as we can find in the code. So if the code is interested in the reallocation offset, it is just ignoring those two lowest bits, and they are used for something. For what they are used? The left bit, and this is super important to point, what I said so far is like 99% or even more cases, like typically it is just exactly like I said. This left bit is kind of optimization for a specific, pretty specific edge case. Imagine, and this now I describe this edge case for you to understand why this left bit is introduced. So imagine a situation that you are having a plug that spans multiple bricks. So it obviously can happen that a plug started at some kind, let's call it P as our plug, and this plug started at this brick, but it ends in another one, in the next one. And we would like to calculate, for example, the next address of an object that is here. So we have an object with this address, let's call it A. And we would like to know what is the future address of A. And if you would follow the previously described by me algorithm, we will end in finding this gap, this plug as the closest one to the A, but it is not the one that contains this address, because obviously the real plug that contains this address has started in a previous brick. So we have something here like the closest one, but it is not the one that we are interested in. And that's sad. Like this is edge case, because now we have traversed the whole plug tree inside this brick, just only to find out that it is not the brick that we are interested in, and we should now fall back to the previous brick and again traverse the previous brick and the whole plug tree to find this plug, and from there take another reallocation offset for this address, which is like traversing one and then the first and the second plug tree, which is overhead. Unfortunately, it happens. So we see here exactly the case. We have discovered that this reallocation address is not the one we are interested in, the plug is not the one we should follow, so we are just skipping to the previous brick and start again, go to retry. But there is one small edge case that you can optimize. Imagine that we know that this plug will be reallocated just after the previous one. So we know, because we know the reallocation offset and of this plug, we know the reallocation offset of this plug, we know also the gap size, so we can easily calculate that in the end this plug will immediately follow this plug after compaction. And this is exactly the scenario for which this left bit was designed. The left bit means I know that the preceding plug will be after compaction just before me. So in this case, I do not have to fall back to the previous brick, but I can take this information from this plug and use it as here. Just what I need to do is just to take into the consideration the gap size here to get rid of this gap size, to get rid of this gap into the calculation. But in the end, we are just using this information from the node that we have already visited. So much less traversal, and this is the edge case for which we optimize it. Pretty, maybe it happens, I don't know how often, but just I need to explain everything, so this is why we have this left bit for this particular edge case. Then realign bit, less fancy and less interesting. This is a bit that we need and we store for keeping an information that we need to pad our plug to align it because of some requirements. For example, we need to have a plug that is a multiplication of 8 in size or something like that. and that was the case in case of the 32-bit runtime, when in the large object heap, when we were storing doubles, they were aligned in the double size, not in the 4-byte size. So they required special alignment, and we need to store this information, because then when we will plan to do anything with this plug, we need to know that this plug needs to be specially aligned. So we have this realigned bit used, and it will just make this plug a little bit bigger just to satisfy these alignment requirements. And you will see this is called large alignment in the source code of the GC, so it is double than normal alignment, and you will see this here and there in the source code, and that this alignment pops out sometimes. But let's not concentrate around this a lot, because I have another level of complexity around all that. I said everything I said so far was pretty easy because no pinning was involved. So the GC has a full flexibility when and where it can move our plugs. But we have pinning, and pinnings adds this another level of complexity here. Because what is pinning? Just a super fast recap. You can mark an object as pinned, which probably means this object address is passed to an unmanaged code. So unmanaged code is accessing this address, and that's why we would like to pin it. If it would be not pinned, and if we would allow to move pinned objects, the address, obviously, as seen from the unmanaged code, is not changed, so it will now see after compaction some random data of some other objects, or maybe the whole memory would be uncommitted, so it would be even not valid to access this. So we need to satisfy the unmanaged code requirement that if we pass this address of an object, it will be not moved, and the unmanaged code will be seeing this object as expected. Important side note: even if we are in a non-concurrent parts of the GC, so the whole application is paused, every managed thread is paused, but unmanaged code is not paused, because there is no way of pausing unmanaged code. So unmanaged code is just working, even if the GC is pausing the whole application. So even during pauses, unmanaged code can access our data. Again, that's because of that we cannot move it at any time. So the pinning is for not moving it, and it adds us a new level of complexity, as I said a few times, because now we have also pinned plugs. We have gaps, we have plugs, and now we have pinned plug, a special kind of plug, which is also storing information about pinning. It's simply saying, okay, this plug shouldn't be moved during compaction. So from this perspective, it is pretty easy to implement, because the reallocation, if we are calculating the reallocation offset for a pinned plug, it is 0, and that's all, the whole algorithm. So on the basics of the previously described algorithm, pinning is pretty easy to implement, because it is just forcing the 0 as a reallocation offset for every pinned plug, and that makes it not movable. So we have pinned plugs. So very similarly, and this, as in the previous examples, every plug is preceded by a gap, so we are storing the plug info in these preceding gaps, and the same for pinned plug. We will just keep the 0 as a reallocation offset. We will keep the gap size, because it may be used if the sweep will be decided to be used. And additionally, we store the information about the free space before it if we decide on compaction. The allocator I mentioned previously is obviously considering pinning, so it is considering how to move plugs to not move pinned plugs, and it will be able to track also this information, that if I will move those plugs, in the end, for example, before this pinned plug, there will be a given amount of bytes, a free space before. And that's the additional info that we need to store for a pinned plug. But that's an easy case, because the gap was before a pinned plug. So that was easy case. It just reused the same algorithm for storing plug info in the preceding gap. Things are more complex if before a pinned plug there was a normal plug. It may happen pretty often. We have a normal plug, so for example a single object which is still live, marked, and it is followed by the pinned plug. And now the question where to store the information, because now we have gap, plug, pinned plug, and gap. So in the terms of our generic algorithm, we need to store information about our plug and about our pinned plug. Storing information about plug is easy because it is preceded by the gap, so we are just storing it here. But where to store info about the pinned plug? Because we would like to have our algorithm generic, it is also stored on the object before our pinned plug. The problem is that this object is a marked object, still reachable live object. So in the end, what's happening here is that we are literally overwriting some data of a live object inside at the end of a plug before our pinned plug. This is kind of mind-blowing because we start to destroy data that may be used, but as I said, it is in the plan phase, which is non-concurrent, so the code will not access it because the code is frozen, it is paused. But for the general purpose of making this algorithm generic, it is working like that. So we have this data stored at the end of the plug, but we cannot overwrite it totally with destroying it, because then we need to restore it at some point. So there is this pre-plugged concept. It is just storing information somewhere else on the side for the data that we have just overwritten. So we have pre-plug saved somewhere at 24 bytes, which is just the end of the preceding plug that just has been overwritten by the pinned plug info. That's what's happening. And then if compaction will be decided that we would like to continue with compaction, we will compact this, so we will move every plug by their allocation offset. Obviously pinned plug will be not moved because it is for that, and we will just restore this information from the pre-plug, overwrite it again to the object that we have just moved to restore it to the correct state, and then we can continue with the application because the data has been restored. So pretty a lot of complexity added just because of this pinning. But it is not the end, because and by the way, to store this pre-plug data, we use the data structure which is called pinned plug queue, and we reuse here mark stack. If you remember, we are having a mark stack for the objects to be visited during the mark phase, and out of a sudden we start to reuse the same data structure here, just because it is there at hand, available, so we start to reuse it for this purpose. So if you will be ever following the code responsible for plugs, pre-plugs and plugs in handling for the pinned plugs, you will see mark stack being used besides its name. Then another level of complexity, another problem. We can have a pinned plug followed by a normal plug. So another problem here, because now we have a pinned plug and a plug, and we would like to store information about the pinned plug, and this is easy because it is in this case preceded by a gap, so we can store it at the end of the gap, no problem. But where to store the information about this gap? We have a regular gap here that we would like to store information. We could do that here. but that's a problem, because this object is pinned and its data has been, its address has been passed to unmanaged code. So even if our application is paused in terms of managed code, unmanaged code is probably still accessing this data. So we just cannot happily override this data with our plug info, because we will just make invalid some random errors in our unmanaged code. So we cannot reuse the end of the pinned plug. What is happening in the end? We are creating so-called extended pinned plug. So we are merging the pinned plug and the plug inside into one single pinned plug, and we are keeping this information for both. So the gap size information will be the same, the allocation offset will be for both. We are just merging them into the one entity, and we have extended pinned plug, which means that because of handling of all this pinning in that manner, which even if we have a single object being pinned, we can pin a lot of other objects followed by it, just because we have extended our pinned plug to cover this scenario, which sounds pretty dangerous. That imagine that you have 1 million of marked objects followed by a pinned plug. It means that our extended pinned plug now is over 1 million objects. We will not move them because the whole pinned plug is as extended is not moved. So it would just create a huge overhead of pinning some random object being only unfortunate enough to lie just after the pinned plug. So this is not the good solution. So in the end, what is happening, if it is followed by many objects, we are just splitting it. So it is one of the cases that when the plug is really split into two, and the pinned plug, the extended one, contains only the single plug being added, and the rest of the plug is just a regular plug. Even if there is a million objects, there will be million objects in a regular plug, and then this plug will be reallocated, and the pinned plug is extended only by a single plug, which still may take 1 megabyte if it is an array. So if you have a small object here, and then you have a 1 megabyte of an array here, okay, 1 megabyte array probably will be on large object here, but you can have 10,000 bytes in size of big object here, and it will be also pinned because it is just after a pinned object here. So it will now constitute the pinned plug, our pinned object and one object that is just after it. And this, what it gives us is that now we can store the plug info, the regular plug info, at the end of our extended pinned plug, because at the end of it is in a similar manner not used by the regular code. So we are calling it a post plug. We are destroying the data inside this end of this regular object, overwriting it with the plug info for this plug, and storing somewhere on the side the information that we have saved this post plug with all the data inside, 24 bytes to be saved and reused after the whole compacting is ended or sweeping. So in the end, as probably pinned objects are living in the middle of regular living objects, typically there will be both pre-plug and post-plug, and all this will be splitted in those three entities. So we have our big set of reachable objects. In the middle there is a single object, and that is pinned, and then we are splitting it into a regular plug, with the end of it will be overwritten by the plug info for our pinned plug, which is extended by a single object, just to make it possible to be overwritten by the by the plug info for the regular plug that is living there. So a lot of pre and post plug magic happens here just because of pinning, which is pretty a lot of complexity. Laszlo is asking, the question is, in case of post plug, why not use the first object after the pin? Why extending with the pin plug with one object? Why not use the first object? This is what is in the end happening. So we are using the one object just after the pin to make it possible. I'm not sure, Laszlo, if as far as I understand, I answered this question, but we can always elaborate on Twitter later on, so you can reach me out and then we will discuss, or somewhere here as a comment to this video. So this is slowly the end. As you see, the pinning adds a lot of complexity, and you will see that you should avoid pinning. Pinning avoids another problems because it reduces the flexibility of this allocator. So now the allocator is not able to move plugs everywhere where it would like to move, because there are those not movable pinned plugs. So they reduce complexity. They reduce the flexibility of the plugs movement, which may introduce fragmentation. But also, as you see, there are other consequences. We have all these pre and post plugs memory traffic. We need to copy them, then we need to copy them back again to restore the correct data. We can have another problem of this extending of the pin plug. So out of the sudden, an object that you don't pin starts to be pinned and behaves like pinned because it is just followed. It is just preceded by a pinned object. So out of the sudden you have two pinned objects instead of one. And another problem is that the plan phase is a little bit of destroyed even more during this. So it is even more difficult to analyze object graphs if you are, for example, interested in interpreting data from a memory dump, because now part of object data is not in the object itself, it is overwritten with all this plug info, and you need to start analyze also the stored elsewhere post and pre-plugs to get a data from those objects. So things become pretty much more complex. And yes, Rafał, this is a kind of opinion, not the question, that the post and pre-plugs looks like kind of putting kind of hacks to make this algorithm generic, still using the same concept of using the preceding place instead of trying to overcome in another way. I will not take a side here, but if I will manage to organize Q&A with Maoni, we will have a nice question for her how she feels with this implementation. But as we know, in .NET 5 the pinned object heap has been introduced, so now we have a separate place for objects that are not moved, and all this complexity should slowly disappear because most objects should be allocated there and not on the regular heap. So all this pinning will be probably less and less popular because we can expect moving libraries using the pinning in terms of pinned object heap, not a regular pinning. So we can expect this complexity will slowly disappear. One side note, large object heap, because what all I was describing so far was about small object heap, so for objects smaller than 85,000 bytes, which are sometimes compacted if the GC decides so, or if we force it. Because we expect the granularity of objects, and it is wise to consider compaction there. In case of large object heap, it is designed for small number of objects which are bigger than 85,000 bytes. So we are pretty afraid of compacting because it introduces a lot of traffic. We start to compact and we start to copy from place to place big objects which are over 85,000 bytes. So by default the compacting is not happening in large object heap, but still you can force it. You can use a flag to say the next full GC should compact my large object heap. So the GC algorithm needs to support compacting of large object heap because it is possible to do it. Moreover, in .NET 5 there are scenarios for the very first place when the compacting of large object heap happens automatically. So by the end we need to support it. But it is much less complex there because we expect not a lot of objects there which are big, so we don't care about all these plugs and gaps and bricks and so on, because it doesn't make sense to operate on that level. Every object is just treated as a plug. Every reachable object is treated as a plug. Every not reachable object is treated as a gap. Simply enough. We don't have any brick tables, and it's enough because remember this is a big object here and there, so scanning it is not so much effort. One consequence of doing that is it is still using the managed heap for storing this plug info. So we have small padding between all objects to have a place for storing this plug info there. That's why if you will take a memory dump and analyze the large object heap, you will see objects interleaved by these three objects, and they are just padding, being there in case you decide to compact. If you don't decide to compact, this padding is not used. It takes place because we need to be ready, but it is not used. If we will compact, the optional plan phase for large object heap will kick in, and it will use this free space between those objects to store the plug info. Simple plug info, the gap size or the allocation offset for every plug. So we will have this the same data there. What is the allocation, what is the size of the space before the pinned plug, and so on and so on. But planning of it is pretty fast because, as I said, we don't expect a lot of objects there, so scanning through them should be pretty fast. The only nice finding from it is the understanding why we have this padding between every object in large object heap. Because we wanted to have a generic algorithm that is storing plug info before and plug, so we are having this place added artificially to have it in case we will need it. Okay, so that's all. I don't have a big slide about code because most of the code is huge while inside a huge while to scan objects, the plan phase to do all that scanning. So if you would be interested in looking at the code, you can find plan phase and start there. Two most important methods are the allocator ones, so the ones that are finding the reallocation offset for your plug, and the optional plan large object heap, which is called only if you force it or if the GC forced it. And then the site on compacting that you can look at also to see what is the decision. Whether we would like to compact or not, mostly based on the fragmentation, but I will not cover that here because it is just comparing some numbers and heuristics. And what I'd maybe just now good time for questions. If you have any questions, if you feel something was not covered or not clear enough. I hope that after this, let's say, lesson, you understand the whole planning phase a lot more. What is pretty important to understand is that this whole plan phase is operating on plugs. So this reduces the flexibility of the compaction. So for example, imagine that after this pin plug, you have a somewhere else, after some gap, for example, you have a plug that is 200 bytes. And this unfortunately means this 200 bytes in size plug will not fit here. And it will be just somewhere after this pin plug. It will be just moved closer to this pin plug. It will be just followed by this pin plug after compaction. But we will not fit into 200 bytes in size plug into this because it is too small. And as I said previously, DC has not this power to split this plug into two smaller ones and put one part here and another part after that. Not yet, at least, because it would add next level of complexity. It is just kind of compromise that was decided. That okay, we will have some bigger fragmentation because of that, because there will be some bigger gaps that could be done, but again, it is not so common scenario that adding this complexity of splitting plugs probably will not pay off. And having all those plugs that way is just good in terms of handling the memory access patterns, building all those plug trees and so on and so on. So it is kind of compromise, but you should just take this knowledge after this lesson. GC is planning compaction on the level of plugs, not particular objects, which reduces flexibility and may introduce some fragmentation if pinning is introduced. But also you will see these advices that in general pinning should not be so severe, because you should pin only for super small amount of time, and if you pin an object for short time, there is a big chance that the GC will not happen during that time, so no one will notice even that you pinned something, because pinning is only discovered and used, the knowledge about pinning is used only during the GC. So if the pinning is very fast, no one will notice, or for a very long time. So those pinned objects will be promoted somewhere to the generation 2, which is now changed so fast, so common, so often. So also the overhead of it should be not big, and we don't garbage collect the Gen 2 often, so also the impact should be not big. So that's the advice: pin for only very short amount of time or very long amount of time. And that's why GC team is not so concerned maybe about this overhead. And as I said, also pinned object heap has been added recently, so even better. Now we can move our pinned objects to the different place, which will be just handled totally differently. It just is not considered during compaction, and all this overhead of pinning is gone. Okay, that's all from my side. And any questions? Just give you 10 seconds for questions if you have any. If you have not, still thank you very much for being with me, for the patience listening to all this super advanced stuff, and maybe not so advanced but pretty deep stuff inside the GC. I'm super happy that I could share it to you because they are not so often covered in documentation and various articles. So I find it super interesting to explain it and to understand how it works internally. And it even gives us some practical knowledge. So that's nice. And okay, one question. So pinned object heap is different because if we are compacting, we are just ignoring pinned object heap. So the simplest way of not moving object is not considering compaction in such place. And if we have a separate object, separate memory region, which we call pin object heap, then we are simply not compacting there, and it means objects are pinned by default because no one will move them. So that's why we don't care about all this stuff there. Okay, it was very nice to be with you with this hour and half. How much of this is covered in my book? I would say 65–80%. I'm updating these slides and knowledge with the additional edge cases, with some newest additions to the .NET runtime, so it would be around 80%. The whole concepts are the same, but some things are added here and there in a textual manner instead of the video. But my book in general consists of this part, which is theoretical, but it is interleaved with the practical consequences and diagnostic consequences. So those videos here are designed to be only about the theory and all those internal stuff, and it still takes hours to cover that. So this is a kind of part of the book that I'm just putting here as a video form on YouTube. Okay, one announcement. I'm taking 1 week off because next week I'm having a medical treatment which requires hospitalization, so I will be not available. We will see in 2 weeks if this treatment will be successful. And so we can take a 1 week break and analyze all those videos. If you haven't watched some previous video, just watch it because it is all required to understand all the .NET GC internals, and all those bricks are cooperating with each other. Okay, so not delaying it more. Have a nice evening, have a nice day, depending where you are, and see you in the 2 weeks. Have a nice rest of the week. Bye. And thank you for all the questions and for being there, as always.